Hello and welcome to Unit 6, Part 5. My name is Mr. Bell and today we're going to talk about exponential growth and exponential decay. So far in algebra, we've talked about linear functions which have a constant rate of change and form straight lines. That's why they're called linear functions. We've also touched a little bit on something called a quadratic, which makes a parabola shape. Now this particular unit, we're going to talk about exponential functions. Exponential functions, generally speaking, start out with a slow rate of growth or decay and then rapidly shoot up really quickly, or start off slow and then rapidly decay very quickly. And we're going to use that concept in this formula above to work some problems out dealing with exponential growth and exponential decay. This is the formula for exponential growth or decay. We'll use this particular function when we want things to grow very rapidly or decay very rapidly. And let's talk about some of the parts. Components of the exponential function formula. A, this number in the very front, A represents the initial amount. Basically, it's whatever we start with. It could be the amount of money in a bank account. It could be the number of bugs in a particular population. A is wherever we start with. R represents the rate, either the rate of growth or the rate of decay. And the rate is generally represented as a decimal in this particular formula. For example, the rate may be 1.5, just for an example. And 1.5 is representative of a growth function, or a rate of 0.4 is representative of a decay function. We'll talk more about how to tell by how much did it grow or by how much did it decay later, but your reference number to this is it above, is it greater than 1, or is it less than 1? That's how you can tell if a particular function is going to be growing at a certain rate, with a growth rate being greater than 1, or decaying at a certain rate, which would be a value less than 1. And of course, the t represents the amount of time that we're looking at. Did our initial amount grow at 1.5% for 10 years, so to speak? So these are the different parts of the exponential formula. Now let's take a closer look at some examples with real numbers and see if we can figure them out. Let's take a look at an example here. This says the exponential growth or decay formula is represented by this, which we talked about on the previous slide. Identify the meaning of the parts. So this is an actual one with numbers in it. And let's see if we can identify the different components. Well, A, remember, represented the starting amount. In our case, we started with 100 of whatever it is that we're looking at. The R represents the rate, either of growth or decay. In this case, our rate is 1.55. Now, I'm going to come to the side over here and talk about rate for a second. We talked earlier about if the rate is greater than 1, it is a growth. If it's less than 1, it is a decay. So in our case, 1.55 is greater than 1, and it is representing exponential growth. You may also have to convert or be given a percent of growth. The way you do this is you figure out how far from 1 is my rate. Well, this one is 0.55 from the 1. To convert this decimal into a percent, you move the decimal to the right 2 places. So 1.55 represents 55% growth rate. Okay? We'll do some more examples with growth rate and decay rate in future slides. The t in this case, it represents the time, which is a 5. And recall that the f of x is what the final amount will be. This is what the final amount will be after we take our 100 starting population, We grow it at 55% growth, which is a rate of 1.55 for a period of time being 5 years. That would give us our f of x, our total after the calculations are done, which is 894.7. On this slide, we're asked to identify growth or decay. So where you will look is where the R is in the formula, which is the rate, and you're going to decide, is it greater than 1 or is it less than 1? In our first example here to the left, our rate is a 1.05, which is a number greater than 1. So this represents a growth function, exponential growth. The second one has 0.75, which is a value less than 1. So this represents an exponential decay function. And the third one is 0.9, which is also less than 1. So this represents an exponential decay function. On this slide, you're asked to identify the rate of growth or the rate of decay as a percent. So if you look at the first example on the left, 1.05 is the rate. We should recognize that by now as a growth, but the question asks for how much as a percent. So how far is 1.05 away from the 1? Well, it's 0.05 more than 1. To convert it to a percent, you move the decimal over 2 places, meaning this represents a 5% growth. Second example, 0.75. Remember, the reference was how far is it from 1? Well, 0.75 is 0.25 away from 1. If you did 1 minus 0.75, that would give you the result of 0.25. Now, to convert that to a percent, move the decimal over 2 places. 0.75 actually represents a 25% decay rate, meaning it's going to be getting smaller very rapidly. And the third example is 0.9. The reference number was 1. Since it's smaller than 1, we know it's a decay, but by how much? 0.9 is 0.1 smaller than the whole number 1. If you thought of this as money, 90 cents is 10 cents away from $1. So now we need to convert 0.1 to a percent. We'll move the decimal over 2 places. Remember, when you move it across a place that's not there, you add a 0. So 0.1 represents 10%. In this case, 0.9 is a 10% decay rate. On this slide, you're asked to actually write an exponential equation for $2,000 that grows at 10% per year for 20 years. This sounds like someone's savings account. So the way we'll set this up is our starting amount. Remember, our starting amount represents our A. In this case, we started with 2,000. We're growing at 10% per year. Well, they gave us the rate as a percent. It's growing at 10%. Well, now you've got to figure out how to write that as a decimal to go back into our exponential function. So to go from percent to decimal, 10%, you'll move the decimal 2 places to the left. 10% is actually 0.1 or 0.1 as a decimal. And remember, it's always being referenced to the 1. So if we're growing, this would be represented by 1.1. Okay? We know it's growth because it's greater than 1, but by how much? It's 0.1 more than 1, and 0.1 is the same thing as 10%. And then for the period of time, which is 20 years. So what we've done is we've set up a function, exponential function, that represents a $2,000 starting amount, 10% growth rate, which was 1.1 as a decimal for 20 years. All right, hope this helps, and thanks for watching.